Continuing on, a photograph of this type of interference pattern is shown right here. And you can see that you have the alternating maximum and minimum that is, in these interference patterns are called your normal diffraction pattern associated with that. Now, waves from slits 1 and 2, which extend into and out of the page, combine at any point P at some distance. And for this distance here being much greater than the distance between the slits, you can approximate those as being parallel at angle theta equal to the central axis. So the conditions for the minimum, I'm going to try to shift this down just a little bit here so you can see the full equation. Well, okay, I guess that's not going to work. But anyway, for the conditions for the maximum are d sine theta equals m lambda, where m is 0, 1, 2, etc. Depending upon where you are on this. And for the minimum, that's d sine theta equals m plus 1/2 lambda. Okay, so those are the conditions for the maximum and the minimum intensity as you are for your different diffraction patterns. So let's check on that. For here you've got this figure where the delta L as the multiple of the wavelengths and the phase difference in wavelengths for the two rays of point A are a third side maximum and a third minimum. Okay, what is the delta L on those? And what happens is for the first condition, the third side maximum, the delta L has to be 3 lambda, because we're doing this in terms of lambda. And so that would mean that the phase difference would be a factor of 3. And the third minimum would be 2.5 lambda, and 2.5 would be the phase difference. You'll notice that's for whatever your n is, because the minimum is 1/2, is less than what that full number would be. So the maximum is at 3 for the third. The minimum for the third one is at 2.5. Okay, practical exercise number 4. This is problem number 14. And in this here we have that double slit arrangement. We're looking at some point P out here. And this distance is 100 times the wavelength, the slit difference here is 100 times the wavelength of light passing through it. What is the angular separation in radians between the central maximum and an adjacent maximum? And what's the distance between these maxima on a screen? And that's D over here is 50.0 centimeters from the length. Okay? So, for the adjacent maximum, we set m equal to 1 in this equation. Okay, so because m equals 0 would be the central one. D sine theta equals ml is the equation that we have for determining where that the relationship or what that diffraction pattern looks like. So that means theta 1 for this first one, the first central one for m equals 1, would be the inverse sine of m lambda divided by d, or just an inverse sine of 1 lambda over 100 lambda, right? So it's essentially the inverse sine of that. In terms of radians, that's 0.010 radians. Now, since y1 equals d tangent of theta, looking at that figure back here, you can see how that works out. Okay, you obtain y1 equals 500 millimeters. Okay, that's the distance between the slits. The tangent of this angle theta right here, which is 5 millimeters. So the separation, Since y is on the axis, there's no separation there. This is the next one separate from that, and so the difference is just going to be 5.0 millimeters. Now, suppose that Young's experiment is performed with a blue-green light of wavelength 500 nanometers. So now we have a lambda value there. The slits are 1.20 millimeters apart. That's your small d. And the viewing screen, the big D, is 5.40 meters from the slits. How far apart are the bright fringes near the center of the interference pattern? So, for a condition of a maximum in the two-slit interference pattern, we have this value right here, where d is the slit separation, lambda is the wavelength, m is the integer, and theta is the angle made by the interfering rays. Since theta is small, sine theta is approximately theta in radians, okay? That's a key assumption there, and it's important that it be measured in radians. Then theta, instead of doing the sine theta, is just m lambda divided by d. And the angular separation of the adjacent one is given by, delta theta, good grief, keeps jumping on me, lambda over d. So the separation on the screen, a distance d away, is given by delta y equals the distance times the change in that angle, or lambda d over small d, or just 500 times 500 times 10 to the minus 9th, that's the nanometers, times the 5.4 meters, divided by 1.2 times 10 to the minus 3rd meters for the small d. And that gives you 2.25 times 10 to the minus 3 meters, or 2.25 millimeters. Now when you have the interference and double slit intensity, so instead of just looking at the interference pattern, we're going to look at the intensity associated with that. If two light waves that meet at a point are to interfere perceptibly, both must have the same wavelength, and the phase difference must remain constant with time. In other words, they must be coherent. That's what coherence means. Same wavelength, phase difference about 0. So a plot of this equation is shown right here. And you can see m for the maximum is shown at these points right here. Here's your first maximum, your next one out for m equals 1, for m equals 2 for this maximum. Likewise going in this direction away from your center axis. Now for the minimum, you can see you have one here just at pi, one at 3 pi, one at 5 pi. And here you have 0, 1, and 2. And so the minimums are at the 0 and the odd different ones. The maximum are at the these other ones right here. Okay? So, So as shown in this, I equals I0 cosine squared of 1/2 phi, where phi is 2 pi d over lambda sine theta. You may have to look at that in terms of the screen there, because it's not in terms of the overheads that you watch along with this, because you won't be able to see it on this particular slide. Okay, but those are two key equations. I equals 4 I0 cosine squared 1/2 phi, where phi is 2 pi small d over lambda sine theta. Now, each of 4 pairs of light waves arrive at a certain point on the screen. The waves have the same wavelength. At the arrival point, their amplitude or phase differences are given by this right here, 2E0, 6E0, and pi radians. 3E0, 5E0, pi radians. 9E0, 7E0, 3 pi radians. 2E0, 2E0, 0 radians. Okay, now rank the 4 pairs according to the intensity of light on the arrival. And the idea here is that if you look at these, go over 2 on one side and go over 6 on the other side, and for a pi radians difference, what you're going to end up with there is that a difference of 4 here, and you'll have a difference of 4 here, okay, because 2 is on one side, 2 on the other side, it's a total of 4, okay? And so this right here and this right here would be equivalent, because this is 0 radians here. Likewise, these right here are odd in both of these cases. These are a matter of only 2 difference in each case, okay? And so what happens is you're going to have A and D are going to be equal, and then B and C are going to be equal. If you want to draw out the phasors like they suggest, you'll see that that's exactly the case. Practical exercise number 6, you've got 2 waves of the same frequency. Oh, and this is problem number 29. Did I mention that problem number 5 was problem number 19? And practical exercise number 4 was problem 14. If I didn't, practical exercise number 3 is problem number 8, in case you wanted to look back at those. But anyway, practical exercise number 6, and this is problem number 29. You've got 2 waves of the same frequency. They have amplitudes of 1 and 2 respectively. They interfere at a point where their phase difference is 60 degrees. What is the resultant amplitude? Okay. Now this one, if you have E1 equals E10, where E0 is the value that they gave you, 1, and E2 is E20 sine omega t plus phi. Okay? So this is your original one. This is the one that's separated from that by this angle phi. This is the phase difference. And phi, as they mentioned, was 60 degrees, right? So the resultant field is going to be E1 plus E2. And so the summation in the H direction is E10, E10 cosine of 0 degrees plus E2 cosine of 60 degrees. So that is 1 plus 2 times the cosine of 60. And the cosine of 60 is 0.5. So this is going to be 1 plus 1, giving you 2. E sub v is going to be E1 sine 0, which of course is going to be 0. E20 now times the sine of 60 degrees. And so that's going to be 0 times 2. Okay. Yes. The sine of 60 degrees is 0.86. Okay. So they lift some things off, sine of 60 degrees. And so the total of this one right here is 1.732. Okay. That's 1.732 is what this is going to equal when you have the sine value of the times 2 of 0.86 times 2. Then to get the magnitude, you take the square of these 2 values, the 1.732 here and the 2.00 here, and that gives you the magnitude of 2.65. To get the angle beta, that's the inverse tangent of this 1.732 divided by the 2 to give you a value of 49.9 degrees. So that your overall equation then, this is what you're looking for there. This right here is your E0 value, 2.65. It's your magnitude. Sine omega t, and then you have your phase difference between them, 40.9. Okay? So that is what it all works out to be. Now, find the sum of the following quantities. Y1 equals this, Y2 equals this, and it's the same exact type of one where you have set this cosine of 30, and we're going to have to stop there, aren't we?